Hello everyone, welcome to DevStandup session 12. And today our guest speaker is Utsav Talwar. I'm gonna give a bit information about our guest. Utsav Talwar is a solution architect at MongoDB, working at the intersection of data and AI team. He helps the teams design intelligent systems that combine vector search, retrieval augmented generation, and scalable cloud architectures. Apart from that, his focus is on the transforming Gen AI concept into production-ready applications that deliver measurable business impact. And today, Utsav is going to talk about his published article at official MongoDB website, which is named as Building a Scalable Document Processing Pipeline with LlamaParse, Confluent Cloud, and MongoDB. So, interesting topic. I would like to give the microphone to Utsav, and he can kick off his presentation. So, Utsav, you can start.
Thank you, Elnur. Hello, everybody. Greetings to. Basically, I think a very good introduction was given by Elnur. My main agenda is basically to help companies build Gen AI application, and there has been a lot of hype, I guess, around Gen AI. And I also understand that a lot of people don't understand what is Gen AI, but they want to implement Gen AI because it's where the hype is right now. And we saw in the past as well, like cloud was a hype, and people started using cloud at a very decent pace, and that's where it has reached to right now. Gen AI can also reach to that level. I mean, that it won't be a surprise. And we have seen how gracefully it has been making changes and how it is being, implementing new stuff like and AGI, we don't know. It might be coming very soon, right? So that's just a bit introduction about me. What I want to discuss today is about the Gen AI at scale. I want to talk about how the Gen AI started. We will be covering about the past, the present, and the future as well. Where the Gen AI, where the Gen AI is headed, where the train is headed right now. So let's start from the past, like where it all began. What was the main area of focus and how the Gen AI got introduced, right? So, like every story has an origin, and for Gen AI, it was the GANs, it was the generative adversarial networks where it all began, right? So, if you were to imagine like two different artists sitting in a room, and one could be a generator, one is a discriminator. Discriminator is somebody who is like a judge, who is always judging whatever the generator comes to him with a new image. Like there is a real image already in the database, and generator would look at it. It will try to imitate that image, and the discriminator is the one who will judge if this is something that I can differentiate between, right? So if the discriminator is able to discriminate, like this is not the real image, this is a fake, and generator is trying to build out a fake image, then it will be like a loss function for the discriminator as well as the same goes for the generator as well, right? So this goes on for multiple generations. Like it's not just the generator will generate one or two images and it will reach to a perfection level. That's not like it. But it will go on to multiple generations. Like it can go to 100 or 1,000 or many multiple generations. And at the end, it will basically reach out to a place where it is where the discriminator is not able to now make a discrimination between these two, right? Like in the first image that you can see, it's barely anything. It will always start with a noise, and this is a noise that you can see. By the end, it will reach to a stage where it is exactly similar to the real image, right? So the real and fake, there is no concept in this case. Like both the images are looking exactly the same, right? So the discriminator is basically it's getting failed at this point, right? So what are the use cases that you can imagine with this, right? So this was a few years back that GANs came out into action, and we have seen like a lot of use cases. The top three are listed, have listed here. The one could be you can see you have a set of data, like you are trying to create a machine learning bot, or you are trying to just create a machine learning model and trying to enhance its capabilities, trying to train on or train on it on some data. you have like 10 or 20, that's the data set you have, 10 or 20 rows or something like that. But you want to train it on 1,000 or 2,000 rows of data, right? But that is not possible because you just don't have that data. Now GANs can come into the picture. They can they can synthesize the data that is not there for you, and it can increase the number of test data, test data that you can have to, train your model on. The second thing is, imagine that you have an image and it's very distorted, very distorted. It has a lot of noise and it's not very clear. Uh, GANs can also improve on that pixel by pixel. So for each pixel, then they can identify if this will make sense or this will not make sense. So overall, the quality of the image can be enhanced by a lot, right? So that is also one of the use cases that GANs have. And similarly, since we are able to synthesize a real image, we are able to create deepfakes out of it, and we can create simulations. And I think something similar we are seeing right now with Sora 2 model as well, right? So that has been the past. That is how the GAN started, and you can read more about it on the on Google website itself. They have a dedicated course on how GenAI started, how GAN started, and all. So that comes to that's what the past was. We are now moving into the present. We are now moving into a system where the where the actual meaning of the complete sentence can be understood by a machine, right? The semantic meaning of the language can be understood by a computer. And now that sounds very magical if you talk to somebody like 10, 20 years ago, it will not make sense to them how this is happening, right? Now, what happens here is it's the vector embeddings that are basically playing a major role into this. Imagine like any sentence like this, a quick brown fox, which is written in a plain English language. Now, if you give this to any computer, they will not just understand what is this and how this really maps to anything, right? But it can be converted into something called as a vector embeddings, which is the vector representation. That those are the numerical values that you are seeing on the bottom here. Now, once these vector embeddings are created, they are created on a vectorized plane, right? If you see on this diagram, this is kind of a 3D vectorized plane wherein each word or each sentence can have a meaning. Like chicken in a vast vector plane, you can see chicken sitting right here, whereas apple sitting right here, banana here, and it can be spread out across accordingly. Now, the idea behind this is there are two kinds of there will be basically two vectors if you see. One will be there are two vectors which are very close, like wolf and dog. These will be very close. These are called the similar vectors which are very similar into context and they have very similar meaning, right? On the other hand, there will be two vectors like banana and chicken which are not exactly similar and they have very vast difference in the meaning if you see. That's that's why they are kept farther apart, right? Now, the what the model that is doing all of this is called the embedding model, and if you see here, you can have a lot of different kind of sources. It can be images, documents, audio, or any video, anything it can be. It can then be transformed through the embedding models, which will basically understand your text, understand in the meaning. They will convert those texts into vectorized format, and they will place it somewhere in the vectorized plane. So that is how if you have 100 vectors, 200 vectors, it will be placed accordingly. So two vectors with the same meaning can sit together. Right. Now, once the system was able to understand, or once the computer had an vision of what these vector points are, the next idea was how would you exactly search on top of it, right? So the very first algorithm that came into picture was the KNN, that is K nearest neighbor algorithm. And if you see, like you have a query that you are basically writing to your database or any system basically, you have that query as the target point, let's assume. Now what KNN will do here is it will try to understand, it will try to create a map between each and every single point. Now there are three different ways how you can calculate the distance between two vectors. I won't go into that, but the idea is basically for each and every vector that is sitting on the plane, the target point's distance will be measured, right? So it's basically, if you understand in the computational network, computational ideology, it is taking big of n time complexity. So for each and every vector, it is trying to map one-on-one, and it takes around, I mean, it will basically take 0 of n, O of n time. So if you have like 10 vectors, 20 vectors, 100 vectors, it will make sense. Even to 1,000, it will make sense. But if you increase it to a million or a billion number of vectors, it will just not make sense, right? And that is what is happening today in the industry right now. And I have personally dealt with a number of clients who are using, who want to scale it to a million vectors or even billion vectors. And KNN does not rightly fit into that area, right? So the next thing that popped up was the ANN, which was the approximate nearest neighbor algorithm. The idea here was, since we were trying to match each and every vector, it was giving perfection in giving the results, but it was slowing down the performance by a lot, right? So KNN was that. Now ANN came into the picture with an approximation method wherein it will not consider each and every node, but it will try to predict an approximate vector which is kind of very close to the resultant vector, right? Now there are three different ways that it could be done: tree, hashes, or graphs, right? Now each and every algorithm has a lot of different ways how you can implement it, but we will try to focus on the graph one here. Uh, the graph one is very interesting to me, and I have read into depth about it. It has implementation. One of its implementation is HNSW, which is hierarchical navigable small world, and it comprises of two different algorithms, right? Underneath, the very first is, and this is quite very interesting to me also, but it's the navigable small world. Like imagine um, let's say for example you have yourself and you have somebody sitting in other part of the world. Like I'm in India right now, and there is somebody sitting in the US. Let's say Donald Trump, for example. Now, if you consider the number of ways that I can reach him, it's only up to 6 points, right? There are only 6 degree of separation between us, and that's kind of strange to me if you analyze it, right? I mean, I don't know him personally. I don't know anybody in the US that's very close to him, but there are only 6 people in between us that match me and him. I can talk to those 6 people, and I will basically be able to talk to him. I don't want to, but I might be able to talk to him. But that's the idea. That's how the navigable small world is implemented, right? Now, a very interesting YouTube video has been released. I mean, Veritasium is a video YouTube channel that you want to, if you are interested into that, it clearly explains how this NSW graphs has been implemented, and you can have a look at it. But this is how one of the main principles of the HNSW has been implemented, right? The other is the skip list. Now, skip list is very interesting again because it has since previously it was being implemented on big O of n time complexity, the KNN algorithm, the skip list got introduced, which is now completely searching the different planes into n log n time frame, right? Now, for each and every, let's say, for example, in this case, you have a complete skip list. This is how the data has been structured, right? Now, I want to search for node number 71 or the node which has value 71, right? I can basically go step by step. I can skip half of the list at once, and then I'll be able to reach at the point 71 in just 3 steps, right? The first step is basically, I mean, you can analyze it from the picture itself, but it's basically you are doing one hop, which is at the middle, 31. From 96 to 31, it's just one hop. And then you are doing second hop, trying to analyze if my value is lesser than 71, right? Like I have 91 as the second value, but I want to still search for 71, which is lesser than 91. So I'll skip that node, but I'll go to the next one, then I'll go to the next one. That's how I reach 71, right? I'm not going through all the nodes, but I'm just doing 3 hops, 3 or 4 hops at max, and I'm able to reach 71. So this is how again we were able to navigate one of the layers and then go to the next layer, to the next layer, to the next layer. That is how the ANN was able to identify the right vector in the whole case, rather than just going to step by step to each and every node. Right? So this is the blog post that I was talking about. That's I have published, I think, a year back, and you can have a look at it, scan the QR code, or I think we'll be able to push it in the description as well. So you'll be able to check it out, read through it. It completely explains all the things that I've just explained in much more detail, right? So that is the past. That is how I'll call it the past because it has been like I think 5 years. 2020 ChatGPT got introduced, and we have since then got involved into how the vectors can be embedded and how we can transform data into embeddings and all that stuff. The LLM got introduced, and it has been a lot of the journey has been very tense, I will say, because 5 years and the range of the range that we have gone to, it's massive, right? Now let's focus also on the future. How we think like the future is going to go ahead, right? Now we did talk about the vector embeddings also right now. We talked about how images, documents, and everything are being converted into vector representations. Sitting in between is a vector uh, embedding model. So all these sources, the images, documents are going through basically the vector embedding models, and these are being converted and being pushed into database. The major part that we miss here is since these are multiple different sources, and we are also talking about millions and billions of records that can be added into a database at once. We have forgotten about one thing, which is the scalability of these. How would you basically scale a pipeline which is trying to ingest such a vast amount of data into one single database with minimal fail or with no failure at all, right? So this is where this architecture comes in. This is where I have published an article with LlamaParse and Confluent, and we are trying to put together something which is a scalable pipeline. And since all these services are managed, you don't really have to worry about much of these things, how you scale it and not, but it will basically be able to ingest your data. It will be able to take care of your embeddings, and it will be able to convert it into such a way that your database can handle these requests, right? So, sorry, that's basically what I was trying to understand, trying to picturize in this. Now, there are multiple stages into this. The stage zero is basically where your data comes from. This is the S3 bucket, assuming it can be any cloud provider for that matter, but S3 bucket is where your data is situated at this point. And it's for most of the companies, they have already a lot and lot of PDF documents, a lot of majorly PDF documents or Word documents, whatever. They have stored that data into S3 bucket. And for that S3 bucket to actually have a meaning, it needs to be converted into embedding so a system or computer, an LLM can understand that, right? So that is why that's the stage zero. The stage one comes in where you are now breaking your files into different chunks, and these chunks can then be processed through a pipeline that can be moved to the next stage. We'll talk about the next stage, but what's happening in this stage is basically the the embedding models are basically able to understand how you want to chunk your data, how you want to break it down into different chunks. Those chunks will then be ingested, or, uh, those chunks will basically be ingested into a pipeline that will be converted into embeddings. That's the next stage. And there are, I guess, different companies who are working on into this, LlamaParse being one of these, and unstructured is also one of these. And there is a very popular um, GitHub repository that has been going online right now that's called Dockling. It's a open source project by IBM. You can have a look at that as well. And that I think is one of the repositories which is able to uh, get your data, get your PDF files, and it's able to understand how you can break it down into different chunks, and then it can then be processed into the embedding models. The most important part into this complete red box here is how you are trying to chunk your data, right? Chunking is basically you have 100 characters wide of 100 character wide a length of something. You want to break it into such chunks that it can make sense even after converting them to embeddings. Now there are different ways how you can do it. You can have parent-child chunking. You can have sentence-wise chunking. There is sliding window chunking. There are different kinds of chunking that you can have implemented into this. So that's the basic idea of this red box, what's happening in the stage one. Now, stage two comes in where you have a streaming application, a streaming pipeline, wherein all these chunks are being ingested. That's here, that's the raw topic where we are ingesting all these different chunks. Once these chunks are ingested, these are then going through a Flink job. Now, Flink is again a managed service that is there in the Confluent Cloud. You can use it to create embeddings. The very interesting thing that they have done here is they are able to connect Apache Flink with a connection, with a dedicated connection that's with, in this case, I have done with Bedrock, AWS Bedrock. And in the pipeline, once you have that data ingested into raw topic, the chunk, it can directly go through Apache Flink job and it can be converted into embeddings, right? So the embeddings that we talked about in the earlier slides as well, that's what it is doing right now. Once the embeddings are converted, it is then going through, I mean, this is a scalability operation that we are doing. We are basically shifting it into two different topics. One is raw, it's then sending that data into Apache Flink, and embedding data topic is something we are ingesting or consuming from, right? So that's the stage two where the uh, operation of converting it into embeddings and then pushing it into the next pipeline. That's basically what's happening here. The stage three comes in where we are now able to get that data. We are able to consume that data, the data which has now the embeddings as well as the regular text. Now that data is being uh, again converted into a format which is more understandable to the database. Now it can be different. It can be simple JSON. It can be using Avro serialization also. But it can be, I mean, of your choice of how you want to do it, right? So once your data is converted, you now have the text, the embeddings. If you want to add metadata also with it, you can have like page numbers or any metadata according that makes sense according to your application. That will be there. And at the end, for persistence layer, for persistence storage, you need to add it into a database that is more reliable. You don't want to keep doing this on the fly because embedding generation, it will cost you a lot. It is a costly operation, but you don't really want to keep doing the same file again and again. So that is why we are doing it. We are storing basically into MongoDB in this case for a persistent storage. And this is where the RAG-based application will take the data from. This is where the complete application will be built. This is how the searching will be done. Everything will be handled on the MongoDB side. Now you won't have to go through the entire pipeline again and again. You will have the embeddings and everything stored into MongoDB. So that's the idea. So I think that covers the complete RAG architecture. We talked about this part majorly, wherein you have all the data sources. It's going through a pipeline which is able to handle the scale, and it's able to convert it into something called as dense vectors. Uh, that's one part. The other part is now we will be writing some kind of queries to make a search on top of our existing data. Let's say you have a policy document that you have ingested into. Now you want to ask a question like, is this covered in my policy or something related to that? So that will be your query, which will also be converted into your vector embeddings. Now, these two vector embeddings will be uh, searched based on the ANN algorithm that we talked about, and that's how you get the results. The results are basically sent to the LLM. That's a different story, but that's how the vector searches, that's how the searches are being done. That's how you're able to get your data back, right? So the future is basically simple. I think we all know where the future is headed right now. It's the agents have started acquiring the market space right now, wherein you have RAG is just one agent at this point. You have multiple different agents which are making calls to a lot of different applications at this point, collecting the data from each and everywhere, and then you are able to build out an application. I think in recent launches also OpenAI has talked about You can just talk to the chatbot and ask for a tool like Figma, give me this workflow or give me this diagram, and it will start involving Figma into the conversation, and Figma will take care of over everything. That's agents. And then MCP and A2As, again, the algorithms or the protocols are being introduced wherein you have MCP protocol or agent-to-agent protocol widely being used by the industry right now, and it takes off the heads. I mean, it takes off a lot of uh, um, uh, basically a lot of people are trying to add agents which will have tools. So all these things are being managed by MCP and A2A. That's I think something for the next conversation. Also, we can deep dive into it. And now that's how it's being done. And the next question is basically, do we have AGI coming soon? So I think that's the end of it. That's what I wanted to talk about into this. Over to you, Elnu, if you have any questions.
Yeah, Utsav, thanks a lot about this interesting topics, especially about these models. Uh, I had like a couple of questions regarding your pipeline. The first
Yeah.
question was that like, do you like currently use this pipeline in your work like actively or?
Mhm. No, not actively. I mean, I have been sharing this architecture with a lot of clients right now, and we are in the process of implementing it into their architecture. But I mean, since it has been recently introduced, so we are working on it to implement it with other people.
The question I want to ask that like what kind of actual use cases benefit most from this architecture?
Mhm. So basically, since it will work basically on topics wherein you want to involve uh, a large variety of uh, PDF documents, right? I recently was in talk with one of our customers who wanted to have, I think, 2 billion records inserted into Mongo, right? Now, 2 billion, if you do it one by one, it will not scale at all, and you can't just keep sitting there uploading one document at a time. It waited for create embeddings and then all that. So this is where the architecture comes into play, and this was the primary reason that we had to build this architecture to make clients, make partners understand that this is how you can basically leverage MongoDB and other partners alongside it to create a scalable pipeline to ingest even 2 billion number of records into Mongo very easily.
Okay. And also, how do you handle the failure of this pipeline if, let's say, can it happen like some data inconsistency or like duplicates of the documents if the pipeline is doing some kind of not wrong? I mean, basically having some problems that it can cause issues in
Yeah.
the handling of these chunks or stuff.
Yeah, so basically, since we have introduced only the managed service in this point, there is LlamaParse and there is Confluent Cloud and Mongo. For the most part, I think both the surveys are capable enough to handle the failures at their own end. But if not, I mean, there are again other ways that we can address it as well. As it goes to scale, we can have temporal added into this, which can handle if there is any failure in the pipeline, it can keep retrying it as well. So I mean, there are different ways that we can have it, and it basically depends use case to use case, how you want to scale it, how you want to take it to the next level, basically. Yeah.
Yeah. Yeah, thanks so much. That was it from my side. I hope
Great.
this topic will also benefit other people like who are watching this video and they will apply also in their work. And guys, that was it from DevStandup episode 12. And as you know that every week we are guesting one guest speaker from the industry to share their experiences with others. And if you are would like to be also our guest, we have the description under this video. There's a speaker form. You can fill it up, and our team will contact you. Apart from that, that was it. And take care all, and see you in our next Dev Stand Up. Bye bye.
Thank you.